We have live functional programming with typed holes, and Cyrus Omar is the speaker. I'm also told that Cyrus is on the job market.
All right. So this is joint work with a bunch of folks, Ian, who is here at Popple, and Ravi, my postdoc advisor at Chicago, and Matt Hammer. So live programming environments, they're all about feedback. They're all about providing programmers with feedback about the execution behavior of the program that they're writing while they're writing it, so during the editing process. And you've probably all used a live programming environment. You've done some live programming. If you've ever used a REPL or a lab notebook environment like Jupyter to sort of write a program piece by piece and then get feedback about that piece before you continue and maybe copy that back into your main program. That's kind of a primitive form of live programming. There are, of course, more sophisticated live programming environments. A lot of them are targeted towards application domains where that feedback is actually useful not only to you, the programmer, but to an audience. So there's graphics live programming environments. There's really cool audio programming environment, title cycles. And UI design for live programming is a big research area. But in this talk, I want to talk about a PL problem that really sometimes limits these live programming environments from achieving this goal of providing ongoing feedback, continuous feedback throughout the editing process. And that is, if we want feedback from program execution, well, we need to know how to execute the program that's in the editor. But we typically only know how to execute complete programs, that is, programs that are fully formed according to a grammar and that are well typed according to static semantics for a language. During the editing process, sometimes we have a complete program, but quite often we have an incomplete program, something that doesn't satisfy those requirements. And typical language definitions, typical language implementations don't say anything about those structures. And I want to say that those are mathematical structures. Those are interesting structures with interesting semantics. So that's really what this talk is about. And so what are some examples that I have in mind? So here's a really simple one. If you have this somewhere in your program, well, your parser is going to complain, right? And that means your whole program is meaningless. It can't even be parsed. It certainly doesn't have a type. It doesn't have, and you can't run it. That might be kind of a transient thing. Here's another example, though, where this one's parsable, but it's not well typed, and so you can't run it. Again, that might be kind of transient. You might be just about to apply F, and then it'll be well typed. But what about this example where you're mapping a function F and you haven't defined F yet? You're writing a test before you write the function. You can't run that. It has a binding error, so it's not well typed. And then there are situations where this ill-definedness can last quite a long time. So say you have a very long case analysis, something that as a PL person you probably do quite a lot. You might finish some of the cases and want to work with them, but if any of the cases have a parse error like the third one where there's just nothing there, or a static error like the second one, then the whole program is meaningless according to a typical language definition. If you're doing a large-scale refactoring, this state of affairs can last for weeks at a time, right? I'm sure some of you had that experience. If you change a very basic type definition somewhere at the beginning of your program, and it takes you 2 weeks before you can even start playing with the program again. I just had that experience with the code I'm writing for the last couple of weeks. So how do we address this? We can't deal with this as just text and assign semantics to the text. We need to give it some sort of inductive structure. And so there's this nice technique, this little technical device called typed holes. And what that does is it allows you to, it's sort of like zero in arithmetic, right? It allows you to say, there's nothing here, but I'm going to put something here to indicate that. And so in GHC Haskell, or recent versions of GHC Haskell has these typed holes. You can give them names. So like the underscore something is a hole named something. And then the type checker will give you some useful information about the types and the bindings available at that hole. So that's some static information there. In Agda, you can actually do one better. You can put things inside of those holes so that if there's a type inconsistency, you can talk about what's inside the hole, and that sort of serves as a membrane around that thing from the perspective of the rest of the program. And then you get all these nice editor services like the goal type and the type that you have, and you can kind of squint at those and figure out what to do. In Hazel, which is the programming environment that we're developing, At a paper at Popple 2017, we developed an edit action semantics that inserts those holes automatically. So in Haskell and Agda, you have to insert those holes manually in your text editor. In Hazel, I'll show you just in a second, those holes are inserted automatically. So every single editor state actually has is well formed with this grammar of expressions with holes in it, and it's also well typed because we reify these type inconsistencies as these non-empty holes, those red dots. So the red dots are type inconsistencies. The kind of orange one is a binding error. There's no G is not bound. So in all of these cases, you can you get syntactic form out of these holes, you get static information out of these holes, but you can't run these programs. In Hazel, you couldn't run these programs. Previously, in Haskell, there's a flag you can set to run the program, but the hole behaves as like an exception, like a not implemented exception, which is kind of a typical workaround in languages that don't have holes. And when you hit one of those holes, your program dies, and you can't do live programming with a dead program. So we wanted to solve this problem, and I'm going to first show you what we did in Hazel with a demo, and then I'll talk about the formalisms behind that. Okay, so you can play with this if you want. It's at hazel.org. Make this slightly bigger. Oops. Okay, so when you start Hazel, you get a hole. Each hole has a name. The names are just numbers in the Hazel UI. So this is hole 1, and you can start typing an expression here. So for example, 2 plus, or let's do 2 times 3 plus. And what you're seeing there is as I type, the Hazel inserts the holes automatically. So this isn't a parse error. It's a well-formed expression with a hole 4 there after the plus. You can see there's a type for this expression, even though it's not complete. It's of type num. And so this is a very simple language. It's a Lambda calculus with a few additional primitives. And you can see there's also a result that's been computed for this expression. So this is the sort of new bit that this paper is about. You can see even though there's a hole in this expression, it's not we can run it, and we can do as much computation as is there. So we can do that 2 times 3 computation. This is true even if that computation sort of appears after the hole in the typical evaluation order. So Hazel does have left to right evaluation order, but that doesn't prevent that 5 times 6 from being computed. You'll get to 30 there. Note that we don't do algebraic rewritings. We don't use the properties of like of addition to turn that into 36 plus hole or hole plus 36. Be ambiguous how to do that, and we're trying to have evaluation sort of work the way it would otherwise if the hole were filled. So just wanted to point that out. So that's kind of cool. Let me show you some more interesting things that you can do. So let's define a function f that takes 2 arguments. I'll put type annotations there this time. And it just adds them, and then I'm going to add something else to those arguments. But first, let me write a couple of tests. So I'm going to define a y1 that's applying f to 2 plus 2 and 10, and y2 is going to apply f to, let's say, 3 plus 3 and 20. So this is quite an incomplete program. It's just a bunch of light bindings with nothing after them. There's a hole in one of these function definitions. And you can see the result at the bottom there is not very interesting. It just tells you that, well, if you have a bunch of lat bindings, you don't do anything with them, and you have a hole at the end of your program, you just get that hole in the result. The :1 means instance 1 of that hole. So I'll show you just in a second examples of holes that have multiple instances. So what's more interesting here is if you look at the sidebar, which shows you all the variables that are in scope, f, y1, and y2. It shows you their types. And then it also shows you the values that the results that those variables are bound to in the closure around the hole that your cursor is currently on. So we're not simply producing a result with holes in it, which would not be very interesting. It would just have hole 23 in it. We're recording a closure, much like a function closure, around each of those hole instances in the result. And so that's what's being reported here in the sidebar is you're saying f has this value of this lambda, y1 has this value 14 plus hole 16 instance 2. Instance 1 was in the body of the lambda. Instance 2 is because we applied f to these to 4 and 10, so we did that computation of 10 plus 4 to get 14, and then that 16 from over here shows up in the result as an instance of whole 16. And similarly for y2, we get a different instance of whole 16, and they're different because they have different closures around them. So if we click on one of these, our cursor gets taken to whole 16, and then we see the values of the bound variables x and y from that lambda in the closure that you selected. So 4 and 10 would be, the screen's a little small, but down here it tells you which closure you selected, whole 16 instance 2 of 3, and it tells you how you got to that whole closure from the result. So you started at whole 23, you clicked on a whole closure in y1, and you ended up at that whole 16 instance 2. And you can actually switch between the closures. There's a hotkeys tied to these, so I can go to instance 3, and then I'll get 6 and 20. So you can switch between all the different instances of the whole very rapidly and get concrete values for these bound variables as you're filling the whole. So these whole closures sort of consistent with the purpose of live programming is basically to make sure that your mental model of the program stays consistent with the actual behavior of the program as you go along. And so I'll show you an example in a second where that might be more relevant, but you can see that like you're getting the computations that, the values for x and y that you would expect. 3 plus 3 does indeed compute to 6 in this case. Okay, so let me show you a couple more things. So far I've just shown you programs with empty holes in them. You can also have these non-empty holes which capture these type and binding errors. So if I change this f to a g, well, G is a binding error, so it says here in this cursor inspector area, expecting something in function type, got a free variable, which we're treating as something of the whole type, and we matched that to a whole arrow hole so that it could be used as a function. I'll talk a little bit more about that in a second. And that's fine. That doesn't break the program. If you look here, y1's sort of result is now just G applied to 4 applied to 10. Right? It can't do anything with G. It doesn't know what it is, but it continues on to y2 and that's fine, and you get the 26 plus whole 16. So you don't break your programming environment by just having a binding error somewhere in your program. If you have a type error, if I deleted this 10 and made it a true, oh, it shouldn't work. Oh yeah. I need to change this back to F for it to have the num arrow, num type. There we go. So here again, you'll see the cursor inspector tells you expecting expression of type num got this inconsistent type bool, but that again doesn't break the dynamics of your program, the live programming behavior of your program. Again, you'll see that the result here shows you that what you actually did was you applied F to 2 plus 2 so that substitution happened, and now X is 4. And now that whole lambda is being applied to true, and you can't do that because it's not of the right type. Okay, and one more example. So I mentioned type holes just briefly. If we make a lambda and we leave the type annotation there empty, and then we do something silly with it, like treat f as both a function that we're applying to a number and as a number itself, that's okay. So the reason I'm in the gradual typing session is because these holes in type position are like the unknown type in gradual typing. And so there's no static type error. There's no red boxes here to indicate a problem because you're saying, I'm going to pretend I don't know the type of x, and in fact, I'm going to treat it as this universal type. But what happens if you apply it to a number like 10 is you get a runtime cast error. So it says you have a 10, which is a number that went through this type hole and was being treated as a function of type whole arrow hole. And that doesn't make sense because nums can't be functions, and so this is a cast error. But cast errors also don't cause your program to die. So we want live programming here. So these runtime cast errors actually are treated much like dynamically generated holes. So you just get this like cast error applied to 2, but the rest of the computation, which was actually fine, you can multiply 10 times 10, happened here. So you continued on and computed 100 here. Okay. So that's the demo. I want to show you a more sophisticated example. That isn't quite a small synthetic example like those were. So this is quicksort. We're at the point in quicksort where we've written the base case, we've partitioned the list against the pivot, and we've done the recursive calls, and we're just kind of contemplating how to combine all those pieces of information to produce the result. And then below that, we've written a simple test, or a simple example, I mean, to help us explore. So again, the result there is not very interesting. It's whole one, instance one. It just tells you we went through the recursive case as quicksort in that example. And that's, you know, like one bit of information, but it's not very interesting. Again, what's more interesting is the data that's in the context inspector in the sidebar. So there, when you're in instance one of whole one, you'll see the outer call to quicksort and all the values for these variables that are in scope at that hole. So the pivot was 4, and the tail of the list was there, and the smaller and bigger calls, you can actually verify your mental model that like partition behaved as you expected. The variable smaller is named correctly because those are the elements of your list that were smaller than the pivot, and similarly for bigger. And then the R smaller, the recursive calls, the results of the recursive calls, again, we get holes there because there is nothing in the return position of quicksort, but we get different instances of those holes. It's not instance 1, it's now instance 2 and 3 for the 2 recursive calls. And we can explore, so these recursive functions give rise to these nested hole closures. And so we can explore this nesting by clicking on one of these hole closures, like R bigger, and then the context inspector will change because you switch to that hole closure, and you'll see the values of the pivot and the tail and smaller and bigger for that recursive call. And you can keep going until you get to a base case, and then there's no more holes there. So what this allows you to do is even before you've finished writing quicksort, you can start exploring the recursive behavior of quicksort and start exploring the values of these intermediate calls like partition and the recursive calls. So you don't, this would be quite difficult to do if you had to put something in return position that was well typed, because probably you're pretty close to done at that point. And so these are the kinds of things we have in mind as use cases. You can imagine being, you know, teaching quicksort and having this on your screen, or having this possibly be in students' hands. We haven't done any usability studies. What we have done is a bunch of theory. So let me talk about that. So the paper has a Lambda calculus with holes, and we developed a dynamic semantics for that. So these are the holes. They look a little bit like hot dogs. The holes have names U. Those are the numbers in the UI. The first one there is an empty hole. The second one there is the non-empty hole, the sort of reified type inconsistency. The binding inconsistencies you can kind of treat as empty holes where the name corresponds to the variable name, so that's not in the theory. And then the semantics are defined by a bidirectionally typed elaboration, pair of elaboration judgments that produce an internal term, D, and I'll talk about what's different between the external terms E and the internal terms D. But the form of the judgment is there. So there's two judgments. The synthetic one, the first one, is produces an elaboration D when you're synthesizing a type from the expression E, when you don't have a given type. And this is sort of at the top level, or on the right side of a let binding without a type annotation on it. And then the second one is the type checking, or the analytic judgment, and that's when you know the type, and that behaves a little bit differently. I'll show you the theorem that governs that in a second. But I just want to show you one of the rules, the rule that governs non-empty holes. So that rule says if you're checking a non-empty hole against some type tau, the term inside the hole can have any other type, can synthesize any other type tau prime, and it elaborates to this internal term, which is a hole closure. So a hole closure looks kind of like a hole in the external language, but it has this sigma on it, and that's the environment that's being tracked around the closure. So you start with the identity environment where no substitutions have happened, so you just have each variable's mapped to itself. And then what you also produce as the result of elaboration is this delta, which is this hole context, which maps each hole name to its type and to the context around the hole. And so that tells you something about what that hole has to be filled with. And there's this typed elaboration theorem that just tells you elaboration is type preserving. So I won't belabor that. running out of time. What I will say is this actually, the internal language is a contextual modal. It's a contextual modal type theory, and so the delta there is the modal context. The U's correspond, the whole names U's correspond to meta variables in CMTT, and these whole closures correspond to meta variable closures. And so this is a really nice. So CMTT is the Curry-Howard interpretation of contextual modal logic, and so gives us a nice interpretation of whole closures and gives us confidence in our approach, a logical interpretation of whole closures in terms of modal necessity. So I'll just mention that. One thing that CMTT doesn't have is holes at the type level, and so we have to add those. And as I mentioned, and the reason for that is you can have type annotations in terms, so you have to have some way to represent incomplete type annotations. You can also have holes at the top level, and you don't have an expected type for them, so you have to put the unknown type in the context. And as I mentioned, and as probably most people that were here for the earlier talks know, this corresponds to the unknown type from gradual typing, and so we bring in all that machinery, the type consistency machinery, and this is a cast calculus, so we have these casts. The difference is really in this failed cast. Failed casts don't cause evaluation to stop. Instead, they're a form there that is indeterminate, meaning it can't be further reduced. It just indicates that there's an error. And so the bottom line is we have a dynamic semantics that obeys this pair of type safety theorems. And what's interesting there is that these are type safety theorems for an empty variable context gamma, but a non-empty modal context or whole context delta. And so we're giving an operational semantics for terms that have free meta variables. And you'll notice that in the progress theorem, there's this additional case indet, which means it's indeterminate, meaning it's stuck. There's a hole or a failed cast in elimination position. And then the rest of it is much like kind of standard progress theorem for gradual type lambda calculus. There's this boxed val, which corresponds to the regular values plus these values with casts on them that haven't been removed at the end of evaluation. And you'll notice there's no error, there's no like cast error case in progress because of the failed casts. So to summarize, actually let me skip the summary because I'm running low on time. And so the corollary of this is because in Hazel, every edit state has static meaning. That was our Popple 2017 paper. We also have this corollary that says there's dynamic meaning for every single edit state. Every keystroke that you make in Hazel will produce a new result. And then, yeah, I don't have time. So I'll just mention briefly, there's a hole filling operation as well, so you can continue evaluation after hole filling. I mentioned the related work already. Contextual modal type theory kind of extends partial evaluation to this partial evaluation with respect to something inside that has a context inside a function. And then I will leave our ongoing and future work on the screen as I take questions.
Let's take a bit of time for one or two questions.
Really cool stuff. Have you thought about implicit typing and type inference in this context?
Yeah. So I mean, it's a bidirectional system at its base. That gives you this, and so you notice in the sidebar there was this expected and got sort of format for every edit state, and that the bidirectional structure gives you that ability to have very simple sort of status messages, including error messages. What we have thought about is doing a type hole filling layer on top of the bidirectional system, which uses type reconstruction. So you're gathering these constraints, and what would happen there is in situations like that silly example I showed you where the type reconstruction can't give you a unique solution because you used it as both a number and a function, you could actually just have it stay as a whole, and the UI could give you the options, the solutions that it found, and you could have the user resolve that ambiguity instead of, as in OCaml or something, it picks one arbitrarily, basically, or heuristically. Yeah.
One last question.
Have you thought at all about how to deal with side effects? I mean, in particular, I was wondering, in the example that you gave in the beginning with left to right evaluation order, where you had 2 times 3 plus blank plus 5 times 6.
Right.
If it wasn't 5 times 6, but something that depended on a reference, and then you fill it in with something that writes to the reference.
Yeah, so you can, so the basic semantics of being able to run the program with the holes, you could run a program that has side effects, and it would do the side effects in the order they would have been done, except any side effects that will be in the hole obviously won't be performed. And that hole filling operation, which I kind of had to skip through, is not valid in the setting where there are side effects, because the hole filling will happen after the other operations have run. So if you have a pure language, you can do hole filling and resuming. But in a language with side effects, you can still do this. You wouldn't want to probably do the thing where every keystroke produces a new result, because if you have an external side effect like launching the missiles, you don't want to do that on every keystroke. But you could at least give the user the option to press enter or shift enter or whatever on every keystroke still. We haven't added reference cells or anything to this formalism yet.
All right, let's thank the speaker again.